All right, y'all. So let's get started with the paper two key right here. So the first one is this big graph. We've seen it before. A student is consulting solubility curve where the behavior of several substances dissolved in water is shown at different temperatures. The lines below represent the maximum solubility of a solute that can occur in 100 grams of water at each temperature. Identify which substance included in this graph shows the greatest solubility at 80 degrees Celsius. So when we look at this, we're going to go ahead and identify 80 degrees Celsius right here on our x-axis. We're going to draw a line straight up, and we will see that at 80 degrees, the greatest solubility, specifically on this graph, appears to be NaNO3. NaNO3. However, something to note is that we can identify that KNO3 is going to achieve a greater solubility if we continue to extrapolate this graph. So on this one, uh, we would say our answer is KNO3. So moving on to the next one. Identify which substance shows the smallest variation in solubility at different temperatures. So for this, we're just looking for something that has the flattest line. A flat line would represent that it is not changing regardless of the temperature. And we can actually see that right here. Our flattest line is NaCl, sodium chloride. That doesn't change almost at all. State the general trend for solubility of gases and for ionic compounds in water as supported by the data. We can see that most ionic compounds have an upwards trend with temperature, while most gases have a downwards trend with temperature. So we can just state both of those. Remember, gases are these highlighted with the dotted lines, while solids are our solid lines. So we can say gases decrease in solubility with temperature increase. Solids increase in solubility with temperature increase. I'm just using the dashed lines to represent the same thing as above. Determine the maximum mass of potassium nitrate that would be expected to dissolve in 200 grams of water at 50 degrees Celsius. So at 50 degrees Celsius, potassium nitrate, which we have to remember that potassium nitrate is KNO3. Let's follow that line, highlight it in red, and we'll go 50. So it intersects this line right about 85. Yeah, I'm trying to get this exact. Yeah, so it looks like at 50 degrees Celsius, we have 85 grams KNO3. However, our question refers to 200 grams of water, and our graph refers to 100 grams of water. So we're going to have to double this because this is 85 grams of KNO3 per 100 grams H2O. So if we want 200 grams of H2O, we just multiply the top and bottom by 2, and we get 170 grams per 200 grams H2O. So our answer is 170. Calculate the molar concentration of a saturated solution of ammonium chloride at 50 degrees Celsius. So ammonium chloride, NH4Cl. Let's identify it on our graph right here. Use purple. We'll highlight that line just so we can keep it visible. And it said 50 degrees Celsius. So once again, we'll use that 50 degree mark. And we notice that there's about 50 grams at 50 degrees Celsius. About 50 grams. Now they ask for molar concentration, which is the same thing as molarity, which is equal to moles over volume. So the problem is we don't have mole or volume. Now we can first calculate mole. 50 grams NH4Cl can quickly be converted into moles by dividing by the molar mass. So 1 mole on top, with the molar mass being about 53.5 on the bottom. And we get an answer of about 0.93 mole NH4Cl. So we've got the mole. We don't have to worry about that. Now we just need the volume. Now, as for liquids, generally when we dissolve solids and liquids, when we dissolve solids and liquids, the change in mass is actually not, or the change in volume is not that noticeable. So you have to make an assumption here, and the IB is looking for this assumption. You want to assume volume does not change with added solute. If volume does not change with added solute, our 100 grams of H2O can then be converted into 100 milliliters H2O because water has a density, water has a density or a rho of 1 gram per milliliter. It's kind of like our standard for density. Now, milliliters we can convert into 0.100 liters, which is also the same thing as 0.100 decimeters cubed. Regardless, both of these are our volumes. So I'm going to divide this by 0.1 decimeter cubed. 10, just get the extra sig fig. And I get a concentration of 9.3 mole per decimeter cubed. And that is my answer for this one. All right, moving on to number 6. If 30 grams of ammonia is added to a 100-gram sample of water, determine the temperature required to keep it dissolved. So we just have to find where 30 for ammonia, NH3, we have to find out where that intersects our graph. So we're going to go to NH3. And I'll pick a different color highlighter this time. Let's go blue. All right. Ammonia. We have to find our ammonia. There it is. We have to find 30 grams. And I will use a blue line for this. 30 grams. All right, and it looks like we intersect right here, right about 50 degrees. So for our answer, our temperature needs to be 50 degrees to keep it dissolved. So temp must be, and I'm actually going to use less than or equal to 50 degrees Celsius because for gases, we can go with a lower temperature. 30 degrees will keep more than 30 dissolved, but it has to be at minimum, it has to be at maximum 50 degrees. If it's a higher temperature, the gas will not dissolve. All right. 7. The student is planning to conduct an experiment that requires 100 grams of saturated solution potassium chlorate at 70 degrees Celsius. Determine the mass of solute that will become insoluble when this solution is allowed to cool after the experiment. Allowed to cool after the experiment to 20 degrees Celsius. So this one has a couple parts. Unfortunately, we can't just make the assumption that 100 grams is the whole solution because mass and volume don't work out. We can't make that same assumption we did for the previous one with ammonium chloride. So instead, we are going to first find out 70 degrees Celsius how much potassium chlorate can we have at 70? So I'm going to keep track of this. At 70 degrees Celsius, we can have 70 degrees Celsius and potassium chlorate. So we now have to find that. That is our KClO. Let's pick a different color. We haven't done brown yet. KClO3. So at 70 degrees Celsius, we have about 35 grams of KClO3. 35 grams KClO3. And this is with 100 grams water. We got to keep that in check. So our saturated solution is 35 grams KClO3, 100 grams of water. At 20 degrees Celsius, yeah, 20 degrees Celsius. That one's a bit easier. We have 10 grams. 10 grams KClO3 with 100 grams H2O. So the problem is we have 100 grams total. And what we're actually saying is we're starting out with a solution that weighs 135 grams, and we're ending with a solution that weighs 110 grams. So the issue here is that we are not starting with the same amount that our graph tells us we're starting with. So we're going to have to do a little bit of extrapolation. The way we can do that is we can use mass percents. So we can take 35, and that's grams of KClO3, and divide it by 135. When we do this, what we're actually finding is the percent by mass that our solution is going to be potassium chlorate. And we get about 26%, which means out of our original 100 grams, we are actually starting with 26 grams KClO3. At the end, our solution wants to instead be 10 grams over 110 grams. And so if we take 10 and divide by 110, we find out that our final solution wants to be about 9% by mass potassium chlorate. So we want to end with 9 grams KClO3. So when we do that, we can find that we actually will take 26 minus 9, and we will have 17 grams that solidifies out or becomes insoluble. So it's a little weird and it's a little wonky, but we have to actually take into account the fact that for this one, mass will change when we add solute into it. All right, suggest a method to separate insoluble salt from the solution from part 7 above. And that's easy. When you're separating solid plus liquid, you use filtration. And that'll work. So you can just filter out the insoluble salts. And there it is. So that is the first question. The second question, this one has to do with empirical formulas. So when we're doing empirical formulas, the first thing we want to do is if we know that this is the percent by mass, let's just assume 100 grams. If we assume 100 grams, then 38.1% of that mass being carbon means 38.1 grams is carbon. 7.5 grams is hydrogen, 16.9 is oxygen, 37.5 is chlorine. Then we just do our mole conversions. For carbon, we can do 38.1 grams carbon, divide by 12.01, and this is mole, this is gram, and we will find out that we start with 3.18 mole carbon. We'll do the same thing for hydrogen. 7.5 grams hydrogen. 1 mole over 1.01 grams, and we get 7.5 mole hydrogen. For oxygen, we have 16.9 grams oxygen. In this case, we're not using diatomic, so let's say 1 mole is 16.00 grams, and we get 1.06 mole oxygen. Lastly, we have chlorine. Chlorine is 37.5 grams Cl. Do our conversion, 1 mole over 35.45 grams, and we also get 1.06 mole chlorine. With an empirical formula, we are just trying to find the ratio between our moles because that molar ratio is going to be our subscripts. So the way we can find that ratio is if I said in maybe a different way, if I had the numbers, if I had the numbers 3, 6, 2, 2, I don't know. That would be a ratio of C3H6O2Cl2. But we don't. Instead, we have these numbers down here. Oh, whoops. Instead, we have our numbers down here. So what we're going to actually do is just divide by the lowest one. So what I meant to say is more like if we have a ratio of 4 to 2, we can divide both sides by 2, and we find out that our ratio is 2 to 1. We're dividing by the lowest value. In this case, our lowest value is 1.06. So we take 1.06, 1.06, 1.06, and 1.06. Turns out that's 3, that's 7, that's 1, and that's 1. So our subscripts are C3H7O1Cl1, or because we don't keep ones, we say C3H7OCl. That is our empirical formula. So this one is a continuation from the previous one. Determine the molecular formula if a mass spectrum for this compound shows molecular ion to be 94.55. What they're saying is that this empirical thing has a mass of 94.55 AMU, atomic mass units, or molar mass, whatever. It's all the same thing. So what we're going to do is we're going to take our original one, C3H7OCl, and we're going to find the mass. So we're going to do 12.01 times 3 plus 1.01 times 7 plus 16.00 plus 35.45. And when we add that up, turns out it equals 94.55, which means that our actual molecular formula is in fact the empirical formula. So we have that right here. So we're done. The thing that can make this a little harder is if instead of 94.55, they said something like 189.10 or something like that. And in that case, what we would have to do is take our current mass and use it to divide it from the original one. So then we would take 189.10 divide by 94.55, the mass that we found, and you would get an answer of 2, which in that case, our actual formula would be C6H14O2Cl2. Because our empirical formula is a strict ratio that the molecule will follow. So all we're doing is finding that case where it actually matches up with the mass. So I'm going to highlight this example in red so we know that it's part of the different one, and I'll highlight the original one in yellow so we know it's part of the actual answer. All right, moving on. The trend in boiling points of the hydrides of group 15 is shown in the graph below. Discuss the reasons for the variation in the boiling points in a series of compounds. Now, boiling point is related to intermolecular forces. Now, with intermolecular forces, the stronger the force, the higher the boiling point. And that's because if two molecules are attracted to each other, the stronger they're attracted to each other, the harder it is to break apart. So what we're looking at is intermolecular forces. When we look at intermolecular forces, there are three kinds we look at. We look at hydrogen bonds. We look at dipole-dipole. And we look at London dispersion forces. Now, hydrogen bonds are hydrogen bonded to nitrogen, oxygen, or fluorine, and these are the strongest. So this is a strength. And look at that. We have something with hydrogen bonds. So that explains why ammonia is very high. This PH3, ASH3, and SVH3 do not have hydrogen bonds. So they will not follow a trend relating to hydrogen bonds. Now they do have dipole-dipole. Dipole-dipole is anything polar. Anything polar. Or anything with a difference in electronegativity. And when we look at electronegativity, phosphorus has an electronegativity of 2.2. Arsenic has an electronegativity of 2.2. And antimony has an electronegativity of 2.0. Hydrogen has an electronegativity of about 2.2. So these are not very different in terms of electronegativity. So their dipole-dipole forces are not actually that strong either. So dipole-dipole is not really anything here. Dipole-dipole, no, we don't really care about it here. They don't actually make a trend. In fact, if anything, it would show that antimony should be lower than the other two because, or sorry, antimony would be higher still actually because it has a greater difference. Well, these two would be lower, so that's fine. The last one is London dispersion forces. London dispersion forces are based on electrons. The more electrons, the more electrons, the more London dispersion forces, the stronger they are. And when we look at the periodic table, we have phosphorus and then below it arsenic and then below it antimony. Antimony, it's Sb, I keep forgetting that. And so the number of electrons increases. And so as the number of electrons increases, we see our boiling point increasing, meaning London dispersion forces are increasing. So when we go ahead and write our answer, we need to include all of this. NH3 is high because hydrogen bonds. In addition to hydrogen bonds, while they have dipole-dipole, it does not affect trend. London dispersion forces causes the increase from phosphorus to antimony. So we need to say London dispersion causes the increase as antimony has more electrons, greater force. I missed something here. We should say it's higher because H bonds and H bonds are strongest IMF. We need to make note of that. So while they all have dipole-dipole, it does not affect trend. LDF causes increase from phosphorus and antimony as antimony has more electrons, greater force. Cool. Higher boiling point. I'm just going to add that one in. All right, explain using diagrams why NO2 is a polar molecule, but CO2 is non-polar. All right, so first we have to draw these. So I'm going to draw CO2. It's a little bit easier. The CO2 does exhibit dipoles. There are two dipoles, but they cancel. The dipoles cancel. Moments. Cancel. Now with NO2, when we look at NO2, drawing that structure is a little bit more difficult. I like using the method where we actually count the electrons. So with NO2, we find that we should have 5 valence electrons from the N, 6 from the first oxygen, 6 from the second, totaling 17 electrons. So I'm going to start by writing my central molecule, which will be N. What I will then do is create bonds. Uh, Usually I will start by single bonding each thing and filling in any valence electrons I know to be there. I will then add that double bond as well as a second pair there, which leaves me with, if I count these electrons up, 2, 4, 6, 8, 10, 12, 14, 16. I will add the final valence electron right here. It's a little bit weird. We have this kind of like free radical type electron that's just kind of out there. Now, regardless of this, one thing we can see is that we do have a dipole moment, and we have another one going this way. These dipoles don't cancel. Dipole moments don't cancel. Another just way to say this is that, and this is the easiest one to say that will still get you points. You can say this is symmetrical. And this is asymmetrical. That will still get you the points. All right. Describe the structure and bonding in silicon dioxide. Silicon dioxide, SiO2, is sand, glass, sand, glass. And this is one of those structures that you have to just remember. This is what we call giant covalent. And in giant covalent structures, this is tetrahedral. Another well-known tetrahedral giant covalent structure would be something like diamond. And that's tetrahedral with carbons. But SiO2 is tetrahedral. All right. Sulfuric acid is a monoprotic acid, student titrated 0.25 milliliters of an unknown molarity with a sample of, that was a typo, sulfuric, with 0.0150 mole decimeter cubed of NaOH. The student conducted 3 trials of titration as shown from the data below. So the first thing that we have to do is fill in this graph. The volume added 13.00. The second volume added is 12.70, and I'm just doing the top one minus the bottom one. The third volume added is 12.50. Now calculate the average volume of NaOH added in milliliters from titrations 2 and 3. So specifically, it says right here titrations 2 and 3. We don't think about the first titration when we're doing averages because that's a trial run just to see approximately how much we use. So for an average, 12.70 plus 12.50 divided by 2. That is just an average. The sum of the trials divided by the number of trials, and we get 12.60 milliliters. Calculate the average moles of NaOH added. Well, we've got moles and we have a volume from our previous answer that we can use. The IB loves using previous answers. So we're going to say molarity is equal to mole over volume. And therefore, we can arrange it to mole is equal to molarity times volume. And our molarity, we were given above as 0.150. 0.150. Oh, whoops. 0.0150. And our volume is 12.6 milliliters. Now, this volume needs to be in liters or decimeters cubed. So I'm going to convert that 0.01260. When I do this math, I find that I get 1.875 times 10 to the minus fourth mole decimeter cubed, negative cubed. Keep our eye, oh, sorry, whoops. This is just moles, not mole decimeter cubed. This is just moles, sorry. That is what we were looking for, and that's what we got. The equation taking place is displayed below. Determine the amount of moles of sulfuric acid that reacts with the average volume of NaOH. Well, we already now have the moles of NaOH that we added on average, so 1.8 75 times 10 to the minus 4. Seeing this volume here is a bit of a misnomer because we already did the conversion we needed from volume to moles in the previous one. And this is mole NaOH. Mole of NaOH we can convert 2 mole NaOH, 1 mole H2SO4. I'm using the coefficients for the mole ratio. Mole cancels with mole, and I get a total volume of, or total mole of 9.38 times 10 to the minus fifth mole H2SO4. All right, determine the molarity in mole decimeter cubed of the original solution. Well, we just know that's mole over volume. So I'm going to take 9.38 times 10 to the minus fifth mole H2SO4, and I will divide it by my original volume, which we know from our original question is 25.0 milliliters, which we will convert into 0.025 decimeters cubed to get our original molarity of 3.75 times 10 to the minus third mole decimeter cubed, minus cubed. Apologies. All right. The last question. The complete combustion of isopropyl alcohol, C3H5OH, can be represented by the equation below. Assuming I fully combust a sample containing 15 milliliters of 1.5 mole decimeter cubed isopropyl alcohol, how many grams of carbon dioxide will I produce? So what I first need to do is find out how many moles of isopropyl alcohol we have. So I'm going to use our, again, molarity times volume equals mole. And I will do that to find that we have 1.50 mole decimeter cubed times 0.150, or sorry, 0.0150 decimeters cubed. I will get a total value of 0.0225 mole isopropyl C3H5OH. I can then convert that into carbon dioxide. So we'll do my stoichiometry, 225 mole C3H5OH. I will convert that using stoichiometry into carbon dioxide, 1 mole isopropyl C3H5OH converts into 3 mole CO2. When I calculate this math out, I get it's about, or sorry, you know what? Before I calculate that, we don't want moles of carbon dioxide, we want grams. So we'll do one more conversion. 1 mole CO2 is equal to about 44.01 grams CO2. That's using the molar mass. Now, when I calculate this out, I will get it to about 2.97 grams CO2. That's that answer. In a lab, combustion took place and the carbon dioxide was allowed to escape. The mass loss was 3.95 grams. Assuming the mass loss was carbon dioxide, what is your percent yield of carbon dioxide? Well, percent yield is just our actual over our theoretical times 100. So our actual was, sorry, our experimental over our, sorry, percent yield is experimental over theoretical. Cool. Our experimental showed 3.95 times 100 because it's a percent. Our theoretical was supposed to be 2.97. Multiply that by 100, and we get a percent yield of 133%. Oh my goodness, we made way more CO2 than we expected. But for C, why might the mass loss in this combustion be larger than the predicted mass from the previous problem? Well, when we look at this, we do produce CO2 as a gas, but we also produce water, which means that the mass that we got may not necessarily all be CO2. Some of the mass loss was water. So we can say some mass lost was due to water vapor. Water vapor, not CO2 only. Only. All right, there you go. This is a whole test. Keep practicing and hopefully this helps.